Okay, so this is a continuation of our discussion of Laplace transform under chapter 1. So this is still this one we will be talking about inverse Laplace. So what is inverse Laplace transform? It's the opposite of the Laplace. When we take the Laplace of a function in time domain, we transform it into S domain. Then if we want to go back from S domain to the time domain, then we need to apply the inverse Laplace transform. So it's the opposite of the Laplace transform. So let's take an example to illustrate this Laplace transform. And usually, the inverse Laplace, if you know the Laplace of the certain function, it's easy for us now to go back to that function. So for example, determine f of t. So we want now to determine f of t instead of f of s if f of s, so let's say f of s is equal to 2 over s minus 1 over s minus 1 plus 4 over s plus 2. So solution, so this is now in S domain. So we need to determine f of t. So we have to take the inverse Laplace of f of s. And that is 2 over s minus 1 over s minus 1 plus 4 over s plus 2. And this will be our f of t. So f of t now will be equal to the inverse Laplace of 2 over s. Inverse Laplace of 2 over s minus the inverse Laplace of 1 over s minus 1. Then plus the inverse Laplace of 4 over s plus 2. 4 over s plus 2. So how do we go back to the t domain? 2 over s. Remember, what function is it that when we take what function in t domain that when we take the Laplace, it will result to 2 over s. So if you look at the table, remember the Laplace, what's the Laplace of a constant? Laplace of a constant k. Is it, this is equal to k over s. And it's similar to this 2 over s. So if you take the inverse Laplace of this, k over s, it will be equal to negative, or it will be equal to k. It's the opposite. So the inverse Laplace of 2 over s now will be just equal to 2. And for the second term, inverse Laplace of 1 over s minus 1. So if we go back again to the table, but what function in t domain will result to this format? We have a answer in the table. We derive e. Remember e raised to a. If you take the Laplace of e raised to a t, this is equal to 1 over s minus a. So if you observe, they have the same similar 1 over s minus 1 and 1 over s minus a, where a is equal to 1. So if you take the inverse Laplace, the answer here will also be equal to e. And for the last one, 4 over s plus 2. So it's also the same. It's s minus a. It's e also. It's the same pattern. But your a here now will be a negative 2. So if we take now the inverse Laplace, we apply inverse Laplace. So for the first one, this will be equal to 2. So f of t now will be equal to 2 because the inverse Laplace of 2 over s is 2. If you take the Laplace of 2, that will result to 2 over s. Then minus 1 over s minus 1. This should be e. Your a here is 1. So raised to t. So it should be 1 times t. So if we take the Laplace again of e raised to t, it will result to 1 over s minus 1. And lastly, for that last part, 4, you can just factor out that 4. Then 1 minus s plus 2. Here, your a is negative 2. So this will be e raised to negative 2 times t. So this is now the f of t of that f of s. That's how we take the inverse Laplace of a function in t domain. Let's take another example. what if my f of s is equal to 8 over s raised to 5 plus 1 over 2s minus 3. Determine f of t. So solution. First, yung unang term, the inverse Laplace of 8 over s raised to 5. Then plus the inverse Laplace of the second term, 1 over 2s minus 3. And this is equal to f of t. So f of t will be, what's the inverse Laplace of 8 over s raised to 5? Now, this one, if you remember the Laplace of t raised to n, this is equal to n factorial divided by t raised to, or s raised to n plus 1. S raised to n plus 1. So if we are now taking the inverse Laplace, if we are not taking the inverse Laplace, so what will happen? This should be 8, and this is s raised to 5. So what will be our n here in the first term? Our n should be equal to 4, because the exponent of the denominator is 5, and that is the same as 5 is equal to n plus 1. So therefore, n is equal to 5 minus 1, or that is 4. And if you take the factorial of 4, 4 factorial is equal to, so we can rewrite this, 4 factorial. So if n is equal to 4, so this should be 4 factorial all over s raised to 4 plus 1. 4 plus 1. Or this is 4 factorial is 4 times 3. Or we can just later on input this one here. Then we can now just cancel that. So we don't have 4 factorial at the given. It's 8. It's not 4 factorial. So we can put 4 factorial instead of 8 factorial here. Then you need to divide it by 4 factorial so that it will cancel out. Then you can move 8 at the outside the Laplace. So this will become, let's write this one, 8 over 4 factorial. Then the inverse Laplace of 4 factorial divided by s raised to 5. So it's still the same as this. I just rewrite it. I move 8 outside. Then I multiply 4 factorial at the numerator. But I also multiply it at the denominator, so that I just multiply it by 1. Then look at this one. It's the same as this. And I know that the Laplace of a function in t that will result to this one will be t raised to 4. T raised to, or t raised to 4. Because your n now will be equal to 4. Then for the second one, 1 over 2s minus 3. So we can still rewrite this so that we can apply directly our formulas in the table. So it's similar to 1 over s minus a, which is, this is equivalent to e raised to a t. That is equivalent to e raised to a t. If it's positive, then this will be negative. So plus, minus. But this is 2s minus 3. There's a number that is being multiplied with s. So we need to remove that 2 by multiplying or by factoring out the 2. So 2s minus 3 will become 2s. Then minus here, this will be 3 over 2 because we factor out that 2. So we can do that. So here we have the inverse Laplace of 1 over, or you can now move 1/2 here. So that here will be s minus 3 over 2. So it's now exactly the same as s minus a. Then we can now directly use the formulas. So f of t now will be equal to 8 over 4 factorial. 4 factorial is 24. So that's 8 over 24. Or 8 over 24 is 1/3. 1/3. Then this will be t raised to n. Or n is 5 or 4. Or n is 4. So t raised to 4. Then to the second term, 1/2. Then e, this is e. Our a now here, our a here will be equal to 3 over 2. So the answer here will be positive 3 over 2 times t. So this is now our f of t. Then another example. What if we have this function f of s equals 1 over, we have a quadratic equation or function at the bottom, s plus 5, determine f of t, which is usually in control theory, we always, or most of the time, we deal with quadratic functions. So how do we solve this one? We need to use, there is no formula in the table, there's no exact similar form in the table, Laplace table. So we need to simplify first this one by completing the square. So how do we complete the square? Take the second term, the coefficient of second term, you divide it by 2, then you square it by 1. So 1 over s squared plus 2s. So I will add here, by completing the square, 1 or 2 divided by 2, that is 1. Then you square that 1 squared, or just simply 1. Then I did add 1. So this is still plus 5. So I need to subtract again that 1. So that I will not change the function. Still the same. You just add by 0. Adding by 0 will not change the function. So this will be, if you simplify this, because this is now a perfect trinomial, it's just equal to s plus 1 squared. And this one will be 5 minus 1, 4, or we can rewrite it as 2 squared. So we can write now this as s plus 1 squared, then plus 2 squared. And this is now the function that we will take the inverse Laplace. 1 over s plus 1 squared plus 2 squared. If you look at the table, if you remember, if this s here, the shifting, we just need to multiply. There's a formula in the table of our inverse Laplace or Laplace table at this part. This one, there's s plus a here, s plus a, then squared. Where omega here is a constant. It's the answer. You just need to multiply the answer with e raised to negative at. If it's positive, if it's negative, then e raised to positive at. So it's sine omega t. So we will be using that formula here. That formula is the Laplace of e raised to at sine omega t. This is equal to omega all over s minus a, and you square this one, then plus omega squared. Now, if you look at this, it's somewhat similar with our problem, but your a here will be negative instead of positive. So if we make it positive, negative, it will be minus and plus. So in our problem, it's s plus a. It's not s minus a. So the value for a, if you take the inverse Laplace now, will be equal to e raised to, it should be negative a. Our a is 1, so e raised to negative t. Then we don't have 2 at the top. I forget 2 because it should be omega over omega squared. Our omega is 2 plus 2 squared. So we need to include 2 at the numerator. So I need to multiply it by 2. But again, I multiplied it by 2, so I need to neutralize that by multiplying 1/2. And this will be my omega. This will be my omega squared. And this is s plus a. So directly we can use the formula. It's 1/2. Need to include that 1/2. So the Laplace now of 1 over s squared plus 2s plus 5 is now equal to 1/2 e raised to 80, because it's positive, so negative 80. Negative, our a is 1, so negative t. Then you multiply this with sine omega. Our omega is 2, so 2 times t. And this is the inverse Laplace of that function. Next, we can also use a partial fraction. Another example, if f of s, if we have here, let's say 86s minus 78 all over s plus 3, s minus 4, and 5s minus 1. So this is the case. If this is the case, it's just not, we cannot just complete the square because there's no quadratic equation. But we will be using partial fraction. Let's review the partial fraction. So by partial fraction, we need to divide that into different parts. Then after that, we can now take the inverse Laplace. So there are different cases. Case 1, if the denominator contains, if D contains A s plus b, contains this form a s plus b. So the partial fraction we will be used a all over a s plus b. Then if the denominator, case 2, if this of s contains, instead of as plus b, it's repeated as plus b raised to n. It can be any number. Then the partial fraction will be a over the first one, as plus b, plus another constant b, as plus b, but this time this will be squared, plus that until that number, until n. So an, let's just make this one a1, a2, up to an, all over as plus b raised to n. Case 3, if the denominator contains quadratic, case 3, if this of s contains quadratic, as squared plus bs plus c, or abc are constant, then the partial fraction that we'll be using will be as plus b all over that quadratic equation, as squared plus bs plus c. Then finally, for case number 4, if it's repeated quadratic, if ds contains as squared plus bs plus c, but this is now repeated raised to n. So the partial fraction that we will be using will be a1 times s, a1 s plus b1 all over A s squared plus bs plus c. Then the second one, a2 s plus b2 all over a s squared plus bs plus c, and this will be squared. Then dot 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 until n, an s plus bn all over a s squared plus bs plus c raised to n. So these are the four cases. So in our example here, these are all binomial. There's no quadratic here. So it's either case 1 or 2. But this is case 1 because they are not repeated. So they are all case 1. So if you do the partial fraction, if you copy this one, so this is the process of doing partial fraction. This will be, we can reduce this into a all over this one s plus 3. This is case 1 s plus 3. Then plus b all over s minus 4. Then plus c all over 5s minus 1. So this is the equivalent. Now, what we need to do next is to determine a, b, and c. So how do we determine a, b, and c? There are two ways in doing that. The first one is by substituting values for s, and the second one is by equating the coefficients of the function or the equations. So in this case, we can use substitution for the values of s. We can, first we need to simplify this, multiply both sides. We need to multiply the both sides by the denominator s plus 3 times s minus 4 times 5s minus 1. So this will become 86s minus 78 equals s plus 3 will cancel out. So a times s minus 4 times 5s minus 1. Then for b, s minus 4 will cancel out. So s plus 3, then 5s minus 1. Then lastly, for c, 5s minus 1 will cancel out. S plus 3, s minus 4. Then we can now let s be equal to, in substituting the choosing the value of s, we need to make the other constant abc to be 0. So for example, we can choose here s equals negative 3, so that this term s plus 3 here, negative 3 minus 3 will become 0. This will also become 0, and we can compute for a. So we have now 86 times negative 3 minus 78 is equal to a times your s is negative 3. So negative 3 minus 4. Then you multiply it, 5x minus 1. 5 times negative 3 is negative 15 minus 1. Then you can now solve for a. So then plus 0, 0, plus 0, plus 0. This is 0 and 0 because negative 3 plus 3 is 0. Then the value of a now, based from this, negative 7 times negative 16 divided by negative 336, that is negative 3. So our a is negative 3. Next, for the other constants, let s be equal to 4. So that this will become 0 and this will become 0. A and c will become 0. We can solve for b. So 486 times 4 minus 78 will be equal to 0 plus b times 4 plus 3 times 5 times 4 is 20 minus 1, then plus 0. Then solving b here, this will be 7 times 19. Then you divide it with this, and the answer will be 2. So b is 2. And lastly, for the coefficient c, or the constant c, let s be equal to, we can use, we can 1 over 5. Why? Because if this is 0, 5 times 1 over 5 is 1. 1 minus 1 is 0. This term also becomes 0, and this will remain. We can solve for c. So s is 86 times s, 1 over 5 minus 78 equals, that's 0, plus that's also 0, then plus c times 1 over 5 plus 3 times 1 over 5 minus 4. Then solving for c, c will be equal to positive 5. So we have now the values for a, b, and c. We can now substitute this one here so that our f of s will be a over s plus 3. Our a is negative 3, so this is negative 3 all over s plus 3. Then we have plus b over s minus 4, plus b over s minus 4. Then plus c, or c is 5, so plus 5 over 5s minus 1. So this is now our f of t. So we can take the inverse Laplace of this function because this is the given f of s. We just reduce it here, this given here, we just reduce this one into partial fraction. Why? So that we can distribute that inverse Laplace and we can take the inverse Laplace of the individual components here. So this will be the inverse Laplace negative 3 over 1 over s plus 3. Then I can move 2 here. And this will be the inverse Laplace of 1 over s minus 4. And lastly, 5. The inverse Laplace of 1 over here. This is 5s minus 1. So we can rewrite that. We can multiply, we can factor out that 5 at the denominator. So it will cancel out with our 5 here. So this will become 1, 5 over 5. Then this will become s minus 1 over 5. We did factor out the 5 at the denominator. Then we multiply it with, or we have 5 at the numerator, so it will cancel out. So f of t now. So these are all exponential functions. So the first one, negative 3 e raised to, your a here is, our a here is negative 3 because it's positive. It's the opposite, so negative 3 times t. Then plus 2, our a here is positive 4. A is equal to 4. So this will be e raised to 4 times t. And lastly, plus our a here is 1 over 5. It's positive 1 over 5. So therefore, this is e raised to 1 over 5 times t. This is now the inverse Laplace of that function. Another example here, if example f of s is equal to 2 minus 5s all over s minus 6. You multiply it with s squared plus 11. So anong case to? This is case number 1 or 2. Number 1 and 2. So we can rewrite this into partial fraction, reduce this one into partial fractions, which is equivalent to the first one, a over s minus 6. That is just case number 2. Case number 1. And the second one is case number 3. This is quadratic, s squared plus 11. So we can write this as case number 3 is we need to multiply s plus b in the numerator. So because we have a here, so we'll start with b times s plus c all over s squared plus 11. And the next, we multiply both sides with s minus 6, s squared plus 11. So this will be 2 minus 5s equals a times s squared plus 11 plus bs plus c multiplied by s minus 6. Then we can use the other method that I told you. The first one here, we use substitution. We can use the other one by equating the coefficient. But before we do that, we need to simplify first the equation. So 2 minus 5s equals, we can distribute that as squared plus 11a plus this one. We can distribute also. This is bs times s, so bs squared plus 6bs plus cs minus 6c. Then we factor out s squared. So we have a and we have b plus b s squared. Then next we can factor out s. We have 6b here and we have plus c. This is s. Then for the constants, we have plus 11a minus 6c. Then we can apply the coefficients, equating coefficients. So for s squared, in the left side, we don't have any coefficient for s squared. We can write here 0 s squared. It means the coefficient of s squared is 0. At the right side, the coefficient of s squared is a plus b. So that is equating the coefficient. Next, s squared, s raised to 1 or simply s. To the left side, we have negative 5, the coefficient of s. To the right side, we have 6b plus c. Then lastly, s raised to 0. S raised to 0 is a constant. To the left side, we have 2. To the right side, we have 11a minus 6c. Then we can solve the equations here simultaneously. We can take from the second equation, we can solve for b. b equals 1 over 6 c plus 5 over 6 plus 5 over 6. Or this should be negative 6b. There is a correction here. This should be bs times negative 6. This should be minus. This should be minus bs times, then c times, then minus. So if that is minus 6b, so this is also minus 6b. So this will be minus 6b. And, okay, it's correct. It's 1/6 over c. We move that c at the other side, or in b, and 5 over 6. We can also solve for c here, or a. We can solve for a. What will be a? This will be 2 over 11. And for c, 6 over 11 c. Then we can substitute these two in the first equation. We add them and we equate it to 0. So we can determine c. So 1 over 6 c plus 5 over 6 plus yung a, 2 over 11 plus 6 over 11 c. And this should be equal to 0. So the only unknown here now is the coefficient or the constant c. So solving for c, c is equal to negative 67 all over 47. For b, we can use the other formulas or equations here in solving b, or these two here. B will be equal to 1 over 6 times c, negative 67 over 47, plus 5 over 6. So our b now will be equal to 5 over 6. It's equal to 28 over 47. Then for a, 2 over 11 plus 6 over 11 plus 6 over 11 times c. C is negative 67 over 47. Then this will be equal to negative 28 over 47. Then we substitute this into our equation here. So a over s minus 6, a is negative 28 over 47, and this is over s minus 6. Then plus, here bs times plus c, b is 28 over 47 times s plus c, or minus 67 over 47 all over s squared plus 11. And we can now take the inverse Laplace of this. But before we do that, we can separate again this two part here. 24 over 7s squared plus 11 and 67 over 47 into two parts, 28s over that and that. So this we can rewrite that. So we still to simplify this. We can factor out 1 over 47, 1 over 47. So that here we have negative 28 over s minus 6. Then here we have 20, this is 28, 28s, the 47 is factored, all over s squared plus 11, then minus 67 all over s squared plus 11. The first term is not a problem, it's just e. The second term, this is squared. So we need, remember the Laplace of a cosine omega t. Cosine omega t. This is equal to s over s squared plus omega squared. So we can take the square root of 11, and that will be our omega. But and the numerator, we have s. So it's okay, we can just factor out that 28. So the answer there will be just cosine something. And for your omega here will be equal to the square root of 11. For the second one, we use the Laplace of sine omega t. Sine omega t. And this is omega over s squared plus omega squared. Our omega is still the square root of 11, but we don't have square root of 11 at the numerator. So we will be multiplying square root of 11 here, then we divide square root of 11 here. So the final now, the inverse Laplace of 1 over 47 of 28 over negative 28 over s minus 6 plus 28, or we can distribute that Laplace, plus 28 over 47, the Laplace of, or plus 28, the Laplace of s over s squared plus 11, then minus, we move 67 and the square root of 11, so that we have, so this is inverse Laplace of the square root of 11 all over s squared plus 11. We can now take the Laplace f of t, 1 over 47. This one is negative 28. This is just e raised to our a here. Our a is positive 6. So this is e raised to 60. And plus 28, this one is a cosine, where omega is the square root of 11. So cosine of the square root of 11 times t. And for the last one, minus 67 divided by square root of 11, that is sine. Sine of omega, omega is the square root of 11t. So this is now the inverse Laplace of that function. Then, for the other parts of chapter 1, the initial value theorem and the final value theorem, I will discuss them later on in the steady state part, chapter 8 or something. So this is Laplace, inverse Laplace transform.